Thank you. So, thank you for hosting me here, Wojtek. It's my first visit to Purdue, and I typically ask to have a microphone because I don't like to raise my voice. I did get one, but it's not for you. It's for the fact that they do a recording. So if you don't hear me well, watch the tape. Okay, I wanted to see if you hear me. So it seems that at least those laughing was able to hear me.
Sir, I can hear you, but I'd appreciate it if you're not going to use the microphone as you speak on. Thank you.
I can understand that I don't hear myself very well. So that's why I sit very close when I give talks, when I attend talks. Can you hear me? Yeah, okay. Very good. Is it okay to start, Chairman? Very good. So, you know, someone just asked me, how long have you been working in biology? And I really don't know biology much. But this is not an exception. I don't know anyone that knows biology much. It's a huge field. It's huge. And we have an assumption that if you ask someone in computer science about databases, they never worked in databases, they still can give you something about it. In biology, it's very specific. You know, I went to my first workshop, I think it was in Santa Fe, like more than 10 years ago. And I was only engineering CS type of guy. And we were only like 20 people. It was before the days of systems biology. Everyone was introducing themselves. And the way they introduced themselves, they were all biologists. They said, what I do is I work on system X. Within system X, I'm interested in process Y, and I do it only on Tuesday. It was very specific, very specific. And it came to me, I said, I'm just interested in information. And they all looked at me. I said, I cannot really tell you. So I think this was a strength of biology, and still the strength that people developed ingenious methods to understand what's going on within the cell, within the brain, because of the dedication of people over many years to understand a specific mechanism. It's, every strength is also a weakness because we are trying to understand principles. So that's kind of, that's the last time I raised my voice. That's a message in the talk. Now I'm going, no, I'm going to. So let's do the following experiment. So assume that we have a couple of screws here on the floor, and suddenly there is a fire alarm. And we all leave the building. We go out, and I tell you some jokes, and you tell me some jokes and some stories about Purdue. I know one story is Purdue is very particular about their logo, right? Is it true? Because this morning I took a shower, I saw that even my soap had the Purdue University logo. It was a quite intellectual shower, I must tell you. No, it is a true story. I was planning to bring it to the talk, but then it broke. Anyhow, we go out, we do the fire drill outside, and then it's over, and then we come back to the room, and as we enter the room, what we see here is a car standing here. And we are all amazed by that, and we don't know what's going on. You know, sometimes my host has some miraculous stuff that he can do, but doesn't look that this is one of them. That's a bit too much even for him. So luckily, the camera that was working there was still working while we left the room. And we instead of listening to my boring talk, we can watch a movie and see what happens as it went from a single screw and evolved into a complete machine that can actually, you can drive it around and it's a completely functional. We can watch this movie from many different angles, see any detail that you want. And what I'm claiming is, even if that's the case, even if we watch a movie and I give you funding as much as you want, you will not be able to get the ideas, the principle behind building cars, how cars operate, what's going on in mechanical engineering, and so on. And you see the analogy to biology, because that's what happens in biological systems. We actually get the tape. We do get the tape. We just don't know what to do with it. Example is a nematode called C. elegans. How many of you heard about C. elegans? Okay, that's a good number. So today, more people will know what C. elegans is. That's something that I learned about 10 or more years ago. I met with Paul Sternberg. He's a biologist at CalTech. And that's what he does for a living, is studying C. elegans. C. elegans is so interesting because it has exactly 959 cells. This is not approximately. It's exactly 959. Has exactly 302 nerve cells. And exactly 131 cells are destined to die as part of development. It's so precise that there is a picture which shows a binary tree that represents the cell division going from a single cell to the complete organism. The reason it's on one picture is it's true for every C. elegans. So when I saw that more than 10 years ago, I felt that instead of studying the brain, which I mainly did until then in the work with biologists, maybe I should work on understanding what's going on within cells. Because we actually have the tape and we still don't know what's going on. We have the tape and we cannot answer simple questions, and I'll show you some examples. For example, we don't know how cells know what to do, how they deal with their own identity. We don't know how they deal with time. And we don't know how they coordinate between themselves what to do. In fact, I recently worked with a postdoc and an undergraduate student at CalTech, and we have some interesting results on that. Maybe next time I give a talk, I'll talk about it. It's a bit too early. So that's, you know, those pictures and the BMW are probably the most important ideas in the talk, okay? I will say it for any idea I will present, so maybe you'll remember some. Okay, what next? The other thing is that if you look inside the cell, it looks pretty chaotic. When I studied biology in high school, people said the cell has different things, but basically think about it as a soup. And in the soup there are different ingredients, and you mix it well, and interesting things happen. This is not true. The cell is actually a three-dimensional structure that has a lot of logic and machinery inside and does wonderful things. We are still very far from understanding it. It's basically a set of chemical reactions, and if you don't know chemistry, it's okay. Some of you know chemistry very well, much better than I do. But think about chemical reactions. So we have A plus B gives you C, and there is a little rate constant there. It tells you something about the probabilities that this reaction will happen, and so on. And because we are engineers, we can take chemical reactions and put them in the framework of circuits. In the circuit, every yellow gate is a chemical reaction, and each one of the orange boxes represent where we keep the molecules related to A, B, C, and D. And the way it works, I was lazy, so I colored all of them with the same color, but they are different. So if, say, reaction 1 happens, then we will get 1 from A and 1 from B, and we generate 1 from C. And if reaction 5 happens, then we get this behavior. And things also are reversible, like everything else in nature, almost everything. So if we get a 2, it can go backward. And that's the underlying mechanism. It's stochastic, and that's what we can measure and see. But we actually have no clue what are the principles behind it. So what do we do? So if you look at the effort in biology, it's mainly what you see on the left side, which I called mapping and prediction. What do we do there? We have people that are interested in a very specific system, model system, specific thing within the system, like what I described. And they are trying to figure out what are the key players in this system. They try to understand what are the relevant interaction between the key players, and the success is a predictive model. That's a huge success. But if you look at papers in Nature, just doing the first 2, it's something that is publishable. Namely, if you find A and find B, and you discover that when A and B interact and the cell does that, and you have nice pictures, then it's a big step forward. And slowly but surely, we build a huge description of biology. If you come to my office and you don't know, say you didn't know how to read and write, or maybe just read, and I ask you, what are the biology books in my office? It will be very easy for you to find them, because they are huge. I have small books and I have biology books. The reason they are large is because we're not able to compress our understanding. So we basically repeat the story for each one of them. And there are only a few very small examples in biology where we were able to compress things into some principle. But in general, it's, at first you cannot believe it, but then you get used to it. That's kind of what I went through. There is very little work done on the right-hand side. That's what the kind of stuff that I'm very interested in. And if you come from engineering disciplines or mathematics, that's what we are used to do. So the idea here is to look at the principles, say in gene regulation, to define or to develop some formal language, say a calculus, to describe those systems. And then through that, get understanding and compression. People in biology also in the way, I'm kind of hard on biologists today. So I'm hoping that there is a biologist here that will kick me back, and that's the way I will discover who is a biologist here. But I talk a lot to biologists. They know about it. I'm trying to explain to biologists why it's important to have abstractions. Besides compression, if you look at physics, the success is that if you have a very good abstract system, then you can jump into the abstract system, manipulate the symbols, and not worry at all about physics, and keep doing it. And then at some point, you jump out of the calculus or the abstract system, and you say, if this system is correct or represents physics, then there must be a phenomena like that. Then you go and design an experiment to see if it's really true. Because there are phenomena that we are not going to see in our lifetime, or we will not even think about measuring. So I'm claiming, how do you know that you even do the right experiments in biology? Abstractions will give you a way to explore the space before you even go and do the experiment, beyond the deep understanding and the compression. As I said, that's the most important slide in the talk. Okay? Okay, I did work on the left-hand side, because when I started in biology, I was trying to understand what people do. And what they do is they look at chemical reactions, they find rate constants, and they want to, and they do what in our language we call Monte Carlo simulation. And they want to predict what will happen given the chemical reactions that they have. So, in fact, I worked on trying to make those algorithms more efficient. I didn't plan to do it. I was just trying to understand what they are doing. And as we put the algorithms that biologists use on the board, it was clear that they are very wasteful. They use supercomputers, massively parallel computers. And at the end of the work with Mike Gibson, we actually showed how you can do it with a desktop, because there was a lot of waste algorithmically in the algorithms, in the way they were doing it. And with Mark Riedel, more recently, we even reduced this by another order of magnitude. I will not go into the details of that in this talk, but I also try to help biologists in this way. By the way, when you talk to biologists, at least when I talk to biologists for the first time, what they see in me is a plumber. They see me a technician, a computational technician. They say, we have this data, can you do something with it for me and throw me back the results? So they see me as a resource that I can help them through signal processing or advanced algorithms to solve their problem. They don't see in me someone that can actually understand the principles in biology. And I tell them I don't mind being a plumber, you know. It's okay for me to get wet. I'm not a good plumber. But you know, I like to do more than that. And recently I'm trying to do just more than that. So you probably, some of you, if you are collaborating with biologists, you went through this experience of talking to a biologist and getting data, and they ask you, so can you predict with that? Can you put a model for us? I will not go into that. I have too many bad jokes on that. Okay, that's not an important slide. The question is it sufficient to have descriptive biology? What I'm trying to convey in this slide is, suppose that I'll give you the following data set. You see a person laughing, and I can tell you everything that you want to know about the brain of this person. And I can give it to you for any person in the world. You want it at the molecular level, I'll give it to you there. Every single piece of the brain. Are you going to figure out cognition? I claim that you will not be able to do it. You'll just get a headache, and this guy will keep laughing. It's not enough. And what we do now is we actually try to look at single neurons and maybe 100 neurons. And I think those efforts are crucial, are very important. They have major importance in medicine, for example. So I think we should keep doing the mappings and looking at systems, but we should also see that we have a huge problem going forward. So working on abstraction is not a new thing. In fact, people thought about this issue many years back. Do you recognize any one of those people here? No? I can give you a hint. One of those people was homeless. Who do you think was homeless? The right one on the right or the one on the left? The left guy. Who thinks the left guy was homeless? Okay. Who thinks this guy with the glasses was homeless? Actually, the guy on the left, on the right was homeless, the guy with the glasses. Those guys, you probably heard their names. Those are McCullough and Pitts. The story is very interesting. It actually happened not far from here. Walter Pitts left home when he was 16 or 17. He lived in Detroit. He left home and he went to University of Chicago and he lived in the library. He was homeless and he read books about logic. That's what he did. And so I call him the logician autodidact. The guy on the left, McCullough, was an MD. And he came to the University of Chicago in '42, and he met Walter Pitts, and he invited him to live with him at his home, because he didn't have a place to live. And what they did in the evenings after having dinner is they talked about science. Now, Pitts, since he read a lot and he was very fascinated by Leibniz and the logic of Leibniz and the ideas about universal languages, he tried to see if you can combine those ideas with understanding of the brain. And as a result, we got their paper in '43 about the calculus of neural circuits. It's a very important paper. In fact, it's the first paper that introduced finite state machines, even in engineering. Before that, people didn't look at those kind of models. It then led to work of Kleene and Moore and Hoffman and so on. I'm not sure we need a homeless guy with an MD to create interdisciplinary research, but I think we can do better than that now. But they definitely thought about abstractions, and it's a good example. So I'm going to forget now about the left-hand side and talk to you only about the right-hand side. And let's see what we are doing here. So I want to go take a step back and tell you how come we were so successful in design. So, you know, we have computers here, we have a computer there, we have Pentium chips, we have microprocessors with millions and millions of transistors, and somehow we can reason about it, not get a headache, and make it to work. So what was the key behind it? It will be nice if we could look at something of this complexity and be able to reason about it, namely to have the reverse process. The reason is abstractions and mathematics. I'll tell you about two important people in the process, but basically we were able to go from reasoning to calculus, in this case it's Boolean calculus, to circuits. So we think about ideas, and they end up in physics, and physics can do the work for us. That's the essence of computing. And major breakthroughs were one in the mid-19th century when George Boole connected logic with calculus. The calculus was Boolean algebra. The nice thing about calculus is that it has syntax. So you don't need to be smart to operate within this domain. And the next breakthrough happened with Shannon in his master's thesis. He showed that you can map the calculus of Boolean algebra to relay circuits. Not bad for a master's thesis. So as a result, we can go from logic, which is text, through the calculus to physics, and the physics can manipulate the syntax for us and give us result. Computers don't know anything about meaning or semantics, but they are very good in manipulating rules or syntax. And those were the two key transformations. One to the calculus, the second calculus to physics. Most people are not aware of that because we don't teach it this way. I'll talk more about it. This is a copy from a book of Shannon. You see for the first time how it goes from sentences on the left to expression on the right. Take a look at that if you are bored one evening. And then he actually didn't do a clean job. There were many other people following him, De Morgan, Jevons, Spears, Schroeder, and so on. And finally, in 1904, a guy by the name of Huntington cleaned it up. In fact, the work on the axiomatic system went all the way through to the 90s. I will not go into those details. But we have a very simple system that describes the calculus of this type of logic. This is a copy from a page in Shannon's master's thesis. Up there, he showed how to add two numbers in binary. Then he writes the expressions for them in Boolean algebra. And then down here, he shows how you do the addition, how you implement that. So in one page, he basically showed you the connection. Today, people write 70 papers if they have a result of this magnitude. It was just one page. Actually, it's not page 495. It is copied from the book of all the contribution of Shannon that was edited by Sloan and Weiner. If you want a nice book, again, take a look at this book. It's a very nice book. Who invented the binary representation of numbers? Do you know? Sorry? Maybe he thought he did. No, I'm just joking. Actually, I talked to, there is a book of McCarthy and Shannon of edited papers. One of the edited book with papers. One of the papers there is a paper of von Neumann about computing with faulty gates. So I had lunch with McCarthy, and he told me about the story, how they put the book together. And I asked him, how did you approach von Neumann? I've heard he's not an easy guy. He said, actually, I was so afraid of him that I never talked to him. I sent Marvin Minsky to talk to him about contributing a chapter. But also he told me that the reason he went to work in AI or started this whole area is because McCarthy, by the way, was an undergraduate student at CalTech and in mathematics. And von Neumann came to CalTech to give a series of lectures. And he went to listen to those lectures as an undergrad. And as a result of that, he decided to work in computing. So you never know what happens to you when you go to a talk, but definitely something good happens there. So there are different ideas, but I like to attribute it to Leibniz. This is in fact a copy from Leibniz, one of Leibniz's books that was translated to English. He shows that. He actually talks about the fact that the Chinese system of I Ching is very similar because you have the broken line and the full line. But in terms of the binary representation, I would give it to him. Also, that's from his book. He describes a binary addition algorithm. So he has an algorithm how to add numbers in binary. He even had algorithms for square root in binary, for multiplication, for everything. However, it didn't have Boolean algebra because this is, as you know, is 17th century. Boolean algebra came only 150 years later. He did notice, however, that to compute with binary, you don't need to calculate. You can do it by recognizing different patterns. But he couldn't connect the two because he didn't have the algebra. Do you know when the first digital circuit was built to actually add numbers, for example, in digital, not analog computers? Is it in the 20th century or is it in the 19th century? Who thinks it's the 19th century? Okay, quite a few brave guys. So in fact, it's pretty recent, 1937, only 70 years ago. A guy by the name of George Stibitz. He's a mathematician. He worked at Bell Labs. And in the evening, you know, it's still, he needed to justify why he's doing it, so he decided to do it at home instead of telling his manager how come he's doing those stupid things. So he worked on his kitchen table, and he built an adder for 2 numbers. And his wife, since he was ignoring her for a long time, insisted that he will call it Model K. That's what the story tells. K for kitchen. He also invented remote computing. They actually built a more advanced version of that at AT&T later on. And also he showed how he went to Boston, and through a teletype he connected to the machine in Bell Labs and showed how you put the input in Boston and get the results of computing from Bell Labs through the teletype. So maybe he invented the internet and not Al Gore. I'm supposed to be politically correct, you told me, right? So this was a mistake. Okay, so this is the progress we made. Okay, we went from reasoning to Boolean calculus to circuits. 38 is the last step, but now people don't even think about it, because the fact that we have those transformations, people can sit next to a screen, play with graphical shapes, and design the next generation microprocessor, because we separated between the physics and the logic and the ideas. That's the power of that. In biology, we unfortunately don't have it. So the problem here is that on the left, we have sensory forms. What are sensory forms? Sensory forms are things that make sense to us. That's the way I call it, sensory forms. Text, images, audio, numbers, figures. Sometimes they make sense to us, sometimes not. But definitely only humans can understand those things. So we do experiments in biology and we generate a lot of sensory forms. The question is, how do we go to reasoning about it? And how do we separate between the gazillion details that we extract in biology and the reasoning about what we see? We have no clue at this point. And I think that's a major bottleneck that we have in biology. So I think the key is to develop a calculus for biology. That's what I think we should do as a community. Now, I'm not going to do it probably in my career. It's not only a matter of time, it's also a matter of skill. But maybe someone down the road will do it, but we need to start somewhere. So say that I write an NSF proposal, and I say what I want to do is to develop calculus for biology. It's funny, huh, Jeff? They fund it. They fund it. That's a sad thing, because I don't know what to do. I don't know what to do, because it's Monday morning. I go to my office and I say, okay, I'm going to develop calculus for biology today. So I spend a few hours on that, and I'm a bit tired. I go get some coffee. I'm hungry. I get lunch. I'm getting even more tired. Then I get a few phone calls. I go home. I didn't develop one. So, you know, days go by. They funded my research for calculus of biology, and I have no clue how I go about that. We actually, that's why I recommend that you look at the early works of George Boole and Leibniz and Newton and whoever is your favorite person that developed abstract systems. Because we actually teach people to use abstract systems through recipes, but we don't tell them about how those systems were developed. So how can we expect the next generation to develop calculus for biology if we never tell them how it was done? Or how do you go about that? Okay? So I'll tell you what my approach for at least making some progress on this topic. Have no NSF funding on that, by the way, so you can relax. So here is the idea. I talk to a biologist. It's a lot of fun. I actually really enjoy that. And then I look at stuff that they do, and they tell me about what they see. And some of the things that they tell me about, I notice that they have something which I didn't see before in terms of the principle. Now, this is completely subjective. I see something unusual there that I wouldn't put if I would build a system. That's a purple heart with a 2 question mark. I identify something. Okay, so I had a good day, talked to biologists. They told me biology is doing this stuff. And I said, wow, why is it doing it this way? I would never do it this way. Then I put my engineering hat. And I'm good in design. That's what I'm trained to do. I'm an engineer. So I said, I'll take the purple heart, and I'll try to use it in a system. I'll try to design systems using this new idea. Let's see if it gives me something. Why do I do it? So there are a few reasons. First, maybe I do it and I discover that it doesn't give me anything. It might be because I am just not creative enough. I didn't find a good way to use it. Or maybe it's also just a bug, because biology is happening through evolution, so it doesn't mean that it's a great idea. It's just there, you know. Or another option is suddenly I use this idea and I can design better systems at the best system available in the market. Just because I saw some idea in biology. Then that's a feature. Then I go back. Now, what do I mean by abstractions? When we design things and use an idea, it forces us to develop some kind of an abstract description of this idea, so we can embed it in the design. And we learn how to manipulate it. So through this exercise, I can actually develop some new tools, new mathematical tools, and maybe I can go back and now reason about what I see in biology, because there is something there that I never knew how to think about. So that's my plan. And if someone has a better plan how to develop calculus for biology, please send me email. Because otherwise I'm going to do that or have my Monday depressing mood of having coffee, lunch, and not doing anything on that. So that's my research program for now on this topic. So I'll tell you a couple. We did quite a few things on that. And we don't communicate it this way. But that's kind of the hidden research program. That's what drives what we do on this topic, is this secret here. Okay? Imagine if I put this slide for an NSF proposal. I'm sure it will work very well. Has no outreach, has nothing there. I hope there is no NSF program manager. Okay. Funding used to be a lot of fun, actually, in the past. I can talk about it forever. So I'll tell you about two things that we did. One is cyclic versus acyclic, and the other one is a stochastic versus deterministic behavior. And I will not go into too much depth on that, but I'll give you the flavor. So the first work on cyclic versus acyclic is joined with Mark Riedel, who was a grad student in my lab. He's a professor now at the University of Minnesota. And what we ask is, when you look at biology, you see many cycles. Even for things that are just supposed to compute simple functions. If you look at logic, combinational logic, no state machine, just mappings, you have no cycles. If you open a book on combinational logic, it tells you combinational logic is in a cyclic graph or a cyclic circuit. Cycles are bad. We ask the following question. Maybe the fact that you have cycles can actually help you in reduce the cost or maybe improve the performance. Namely, is it a feature or a bug? Sounds a bit crazy, but that's what we did. Here is why, if you open a textbook, they tell you that cycles are bad. So you have a circuit here with AND, OR, AND, and 3 inputs, A, B, and C, and 3 output. And if you assign 1, 0, 1, then you actually don't know what will be the outputs. Because when you have a 1 on the AND, it doesn't force anything. 0 on the OR doesn't force anything. So you actually don't know what this circuit will do. It can do anything it wants. And the confused guy there is the engineer that designed it because he's going to be fired. So the best approach as an engineer, if you design combinational circuits, do what the textbook tells you and don't put cycles, because it will give you a headache and you need to feed your family. Okay. Here is, so we did this work, and we of course did a lot of literature search. I'm kind of addicted to literature search. So I thought maybe Leibniz did it already. No, he cannot do it. But I found a guy at Stanford called McCow that in '63 did an engineer thesis. You know, people used to get engineer degrees. And in his thesis, he looked at the following circuit. It has a cycle, has 2 outputs, has 4 gates. That's his thesis. He's focusing just on this circuit. And you can convince yourself that it will always have deterministic outputs, because assume that x equals 0, then it forces the AND gate to output 0, and then in fact you don't have a cycle, because the 0 breaks the cycle. If x is 1, it breaks the cycle here. So in fact you can write the Boolean equations related to this circuit. So you can compute with cycles, provided that those kind of things happen. The other thing is he did, which is the bigger part of his thesis, he proved that you need at least 5 gates to compute those 2 functions if you don't have cycles. So in fact, he was the first to show that you can get an improvement factor of 4/5 for this specific function if you allow cycles. I think his work went unnoticed. There were only a few things that were done later on. His friend Short worked on that in parallel Kautz. That was, I think, his advisor. Huffman from Huffman Coding worked on that. And Rivest worked on that in '77. Rivest was the last one to work on that. I talked to Ron a few years back. I said, I wish someone else will continue, but no one really looked at that. What Ron Rivest showed is you can get an improvement factor of 2/3 if you introduce cycles. And what Mark and I showed is that you can get an improvement factor of 1/2 if you introduce cycle, and under certain conditions, that's almost the best you can do. But that's a theoretical result, which is interesting. We went forward, and we actually decided to compete with the best design in the market, in design automation community. So Mark went and got the open source software for designing circuits that is available in Berkeley. He added the condition of allowing cycles, and we have new data structures and algorithms to design circuits with cycles that are deterministic. And it turns out that within this space state space of circuits with cycles that are deterministic, we can do better than the best existing designs. We sent this paper to Design Automation Conference. It's the largest conference in this area. It has 10,000 attendees. And the paper won the Best Paper Award. And I told Mark that's the most welcoming kind of attitude I ever got. Because I never sent a paper there before, and I didn't send one there after. So someone told me maybe the best way to get award is to operate outside your community. So I actually tried it. I sent a paper, journal paper to, we did some interesting work on propagation. I sent a paper to IEEE Transaction on propagation and antennas. The transaction, it won the Best Paper Award of the Year in the Transactions. So it is a good algorithm. My 2 recent Best Paper Awards are outside my domain. Yeah, I'm running out of communities to send it to. I actually don't care about those awards, but don't quote me on that. So anyhow, we showed that it's a feature, and we have all of those numbers, which, you know, the benchmarks, they have funny names. They look like passwords, but they actually mean some specific circuits. And we showed that we can get smaller circuits and can get faster circuits. We tried it even on existing designs, like certain pieces in microprocessor, and showed how to reduce it. We have a patent on that, and there is some interest from some of the design automation companies. So, and it's all started with this little strange system that we look at a feature bug kind of thing. Okay. The second example, and there are papers on that. I can feed you with more details if you want. The other example is stochastic versus deterministic. That's joint work with Matt Cook, who was my grad student. He is a professor in Switzerland now. David Soloveitchik, who is a grad student in CalTech, and Eric Winfrey, that is a professor at CalTech, used to be a grad student at CalTech. By the way, Matt is a student that I accepted to CalTech. The first time I accepted a student that his degree was a high school degree. He didn't have any degree besides a high school degree. But he is an outstanding researcher. I will not go into details here, but you'll hear this name in the future, I'm pretty sure. So I went to many biology talks, and don't tell the registrar at CalTech that he didn't have anything. No, it's okay. So I went to many biology talks, also at CalTech, and people that we work with at CalTech. And they keep talking about the stochastic behavior as noise. And I asked him, how do you know it's noise? Maybe that's what it should do. That's what I used to tell my mom. I said, maybe that's what I should do, you know? How do you know it's improper? And, okay, so it really bugs. I mean, how does it work with a stochastic behavior and still it's precise at the end? You know, what's going on here? So I'll show you some results we got. So I just want to refresh your mind how chemical reactions work. It's a fun thing. If you have time, play with it. It's a different kind of computation model. So we have 2 reactions here. The red one, A plus B gives you a C, and the blue one, C plus D, gives you 2A, which means that you have a molecule from A and B will give you a molecule from C. And you might have millions from each, but that's what it represents, okay? Now, assume that we start in our state space, we start with a starting point, which we have 1 of A, 1 of B, 1 of C, and 2 of D. That's what I mean by 1, 1, 1, and 2. And if the red one happens, then we lose 1 of A, 1 of B, and we get 1 new 1 of C, so we go to 0, 0, 2, 2. The blue one happens, we go to 3, 1, 0, 1. Why? Because we get 2A, and we lost a C and a D. And then here only the blue one can happen, because we don't have A and B, so this reaction cannot happen, the red one. And same thing here, the blue one cannot happen, only the red one. So we actually go to the same state, and then it goes to 4, 0, 0, 0. So that's the state space of this set of chemical reactions. Okay, that's a very simple system. But the way biology works is you have many reactions, you have a huge state space, and that's the computational engine of life. If you figure out a way to deal with those systems, you'll make a huge progress. We are still trying to figure out how to deal with it. So the first question we ask is the reachability question. Given a system, some initial states, in this case, in my example, was 1, 1, 1, 2, and I give you a state 4, 0, 0, 0, and I ask you, starting at A, can the system reach B? This was the question. Of course, you can run through everything, but you have to remember that the number of molecules can grow and it's not bounded. So it's not clear how to deal with it. So we were very happy to show that this question is decidable. This is a computer science department, so I say it with ease. But another way to say it is that actually, even if you allow the number of molecules to grow, there is a way to represent every one of those state spaces as a finite state space. We were very excited about this result, to the point that we almost started writing it down. Then we discovered that it was proven before, in '69, by Karp and Miller, D. Karp, in a context of vector addition systems. So I went to D. Karp, that I know very well, and asked him, do you know that you proved that the state space of chemical reaction network is finite? He said, I never worked on this topic. He actually works in biology now. If you have a chance, go and listen to his talks. They're wonderful. So I told him about this connection. Of course, he understood it in a minute, but never realized that those two are connected. I also basically communicated with him that Matt Cook wanted to tell him that the competition was not fair because Matt was born after '69. Anyhow, in science, you prove things that were proven before, it just gives you more energy. And in fact, our key question was not the issue of the deterministic state space, but the probabilistic one. So here is a question. Typically, things happen with probability. The more molecules you have, the more likely the reactions that use those molecules are going to happen. If we have many A's and B's, it's very likely that A plus B gives you a C will happen. And the reachability question, when we have the stochastic space, is again given a state space, some initial state A and state B, we ask, starting at A, is the probability to reach B, say, bigger than something, 1 minus epsilon or whatever? Is it likely that it will happen? Those are very important questions. Say, if we figure out the connection between certain disease and something that is going on in the genome, then say that we can compute actually the probability that some bad thing will happen related to this disease, given some signature on that. So we don't know how to reason about it. We knew how to answer the question with regard to the deterministic reachability. What did we do with regard to the probabilistic one? So we actually proved that in this case, it is undecidable. It sounds like bad news for people that are interested in solving algorithmic problems. But there are good news for people that want to use it, because it also means that the system of chemical reactions with probability has computing power, like a Turing machine. So the fact that you have stochastic behavior means that suddenly you can get general computation. In fact, it's the first example that we know of that within a certain computing paradigm, the probabilistic behavior gives you more power to compute. Typically, probability helps you in increasing the efficiency in the average case in terms of being able to compute things. So the running time is better. But here it's whether you can or cannot do it. And so basically we showed that probability enables some kind of general, almost precise computation in biochemical systems. Are you nervous that I'm not going to finish? No, you're not nervous? What I do typically with a host or chair is that at this point I have a few slides that say concluding remarks, but I have like 10 more slides. But every time I put a concluding remarks, the chairman is becoming very relaxed because I feel, but then I go and talk about another thing, and then I pull another one just to make them relax. I'll be done soon. He's recording everything, you know, so I need to think what I'm saying here. I'll show you the idea in the proof. It's based on register machines that were invented by Marvin Minsky. Who heard about register machines? Very good. One is enough, you know, at least one person. So it's a very interesting system. It can do general computation. By the way, if you want a really good book, get Minsky's book on models of computation. It's really a wonderful book. So we have two registers. They can be infinitely large. And we have a programming unit that tells the registers what to do. And what Minsky showed is that this can do universal computation with two registers. I'll talk about the programming unit, what it does. It feels closer to our computers than the Turing machine with the infinite tape. So our approach, since register machines are universal, is to simulate register machines with chemical reaction networks with probability. That's kind of how the proof works. So what are the commands in the register machines? It has two commands. One is increment. So you basically take a register and add 1 to it. And the other one is decrement. You basically take away 1. However, sometimes there is a 0 in the register. In case there is a 0, then you jump to a command called K. So the decrement has two operands. One is A is a register and K is a command. So this way you can implement a conditional jump. And just with two registers and those two commands, we can do any computation you want. Non-trivial proof, by the way. Okay, I'll show you an example of a program. So we have three registers, A, B, and C. A and B are non-negative integers. C is 0. And now you're all tired and your serotonin is depleted at the end of the talk, so probably you don't know what this program is doing. But it's doing something very simple. The output of the program is 1 if A is bigger than B. And it's 2 if A is smaller or equal to B. And I show you how it works. We decrement A, we decrement B, we decrement C, we decrement C. It doesn't want to do it. Yeah, now it did it. So it jumps back to command 1, does it again, and it goes this way. And now we get a 0 here. That's interesting. and again go back here. So now we get 3 zeros, and we are in command number 2. So we are going to jump to 5, and the program ends C equals 1. And we know that it's correct. A was bigger than B. It was 5 versus 4. And the way we show the simulation is that we actually have a compiler that can take an arbitrary program written in register machine language and create a set of chemical reactions that computes it. I'll show you how the compiler works. So the increment 1, we have the following chemical reaction. S sub I goes to R plus S sub I plus 1. So we need a substance for each line in the program. But remember, the program is finite. I'll say more about it. The decrement is R goes to S sub I, R plus S sub I goes to S sub I plus 1. If R equals 0, then S sub I goes to S sub K. Now notice that if R is 0, the first one cannot happen. So the second one will happen. However, there is a little problem there. So that's a compiler. And I'll show you on the example, we can get the program I showed you before compiled into chemical reactions. But there is a problem, because you see that this reaction, the R equals 0, can happen even if R is not 0. That's a problem. So it's not, we can implement a straight line program in register machine using chemical reactions. However, we get stuck when we try to implement the conditional jump. And of course, we should have known we will get stuck because we didn't use the stochastic behavior yet. So the way we do it is we actually delay the second one here using what we call the stochastic clock. And I will not go into those details here. You know, who needs to hear about a stochastic clock 5 minutes after the time the talk was supposed to end? Right? Okay. So, so those are the cases. And using the stochastic clock, we can guarantee that if R equals 0, this will happen with probability 1. That's obvious. But if it's bigger than 0, then it will happen with probability which is very close to 1. And it works even if you have a very large program. And that's not, this proof is very clean and approachable, but in fact, we have very much more efficient simulations in terms of the number of reactions using some other ideas. So in fact, you can think about having a system where you write a program in C or in Mathematica or whatever, and then it goes into chemical reactions that operate inside something and do the computation for you. Okay, so I'm almost done. So I talked about the Purple Heart approach, the stochastic versus deterministic. I talk about cyclic versus acyclic. And the other two things we do is we look at relations versus functions. Because we are all trained to think about functions unless you work in databases, where then it's the only place where you think about relations. And I think a lot of what's going on in biology relates to algebra of relations. A lot of what's going on in the brain relates to algebra of relations. So we are actually working on that. And then trying to figure out the logic for things that work with probability rather than for deterministic things. In fact, I'm working with a grad student that got his undergrad here at Purdue on this topic. He just joined CalTech. That's my last slide. I really believe in this statement. I read history books, and I think you can learn a lot from the challenges people had in the past. My daughter doesn't like this statement. She says that that's why I always run into walls, because I try to look back all the time. But I think it's good to understand the work of the people that were at the foundation of information, of what we do, like Leibniz, George Boole. I mentioned Emil Post. If you don't know who he is, you might want to look at his work. Of course, Turing and Shannon. And I think the message is that if we want to ever develop calculus for biology, it should start by us changing the way we educate the next generation. And at CalTech, as Wojtek mentioned, we are trying to change the system and to have a whole focus on information that integrates not only engineering, but also physics and chemistry and biology and social sciences and economics and many other areas. And it seems that there is very strong response of the students. In fact, I'm going to teach a freshman class on that this year. So I'm busy preparing a class that I have too much material for at this point, but at some point it will work out. So I stop here and I thank you for your attention.
Always a set of physically possible molecules that will follow this equation?
That's a good question. So what we are trying to do, you can think of the chemical reaction systems are right now the best interface we have between people like me and people that actually watch the chemical reactions. So the first question I ask myself is, can I take this description and make it compute? The next step is what Shannon did, is can you map any set like this into a physical system? I don't know how to answer this question. There are a few other questions that we are actually studying in addition to that. Because you can think about primitives, right? Rather than having general ones like I had, just have a selected set. And maybe it will be enough. This selected set can be implemented. There is an issue of energy. How much energy are you going to consume to do that? So there are all the issues related to the point where you want to make it physical. And that's actually David, in his thesis, is working on that. That's a very good question. Yes? Right.
Now, if you're thinking about developing some abstract systems for biology, aren't you somewhat dependent on the stochastic systems being large so that their outcome is definable? What if most or some large number of biological processes or evolutionary transformations or something happen in this kind of small number limit? What are you going to do in that sort of system? What sort of predictability are you ever going to have?
In fact, many of the biological systems operate with very small number of molecules. I think that
the systems, well, that's because sometimes stochastic processes do give you, sometimes they do give you differences between large and small numbers, and sometimes they don't.
Right, but de facto is that at least the systems I work with in signal transduction, they operate with something like 400 molecules, or 800 molecules, or 300 molecules. So you cannot look at stable states. You have to look at dynamics. In fact, that's the essence of the Gillespie algorithm and the algorithms we developed later on, that It's not differential equations with looking at stable states. This is a very different game. So I even didn't talk about this part, but I think there is a whole issue there of how do we reason about small numbers and how do we reason about geometry. Because also within the cell, you might have a large number, but they might not be in the important place. They might be in some place and not in another place. So the whole theory of computation is not taking geometry into account at all. Here we have a three-dimensional structure where things are mobilized to one area, then they are mobilized to another area, and not everything is mobilized. So we don't know yet how to reason about that. But I think your question is basically opening another door of investigation, which we are looking into it, but again, it is a challenge. The challenge is that we don't have ways to include geometry in information yet.
Another question? Go ahead.
I still didn't quite get it. What this abstract system looks like? If at the end you get this system about the biology, what the system looks like, how it looks like.
I wish I knew.
Since biology is all this reasoning, it's quite simple. People knows how to, if you know the condition 1, 2, 3, the knows what. Since the biology is complexity comes from this starting condition, it's too many, too different.
Well, if if you looked at physics and didn't have the abstract system we have, say you look at the days where people looked at the sky, okay? That's what and they have different telescopes and they saw the stars moving and they recorded every single movement and it was very detailed. And we didn't have the understanding what's behind this type of behavior. Then that's where we are right now in biology. And if you ask me at those days, how will the abstract system look, I will probably tell you, I don't know. So I honestly, I don't know. If I have some conjectures about what are those mathematical systems and how they should look like, but I really, to be honest, I don't know. And when I talk to biologists and I show them this slide, then they say they are experimentalists and they have a lot of common sense. They have very intuitive people. They look at it, they say, so it means that in 350 years we might have something. Because they just look at the dates. Actually, they say it, it's okay. Okay, yeah.
I think more or less, I agree. I think in principle with many of the things you said, but a couple of points. So at some point, in terms of doing this abstraction, you take the view of an engineer designing a system.
Right.
And one issue there I think that's a bit distinct in biology is that organisms have baggage, they have evolutionary history.
Right.
So I think that's one thing to think about,
right.
or I worry about. And thinking about this, that one can design things more efficiently, they exist, but things evolve in a particular way. And then the second point, that's right, you also talked about descriptive biology, and I think that's a phase biologists have to go through, but I think a lot of biologists are definitely behind the idea that we need more theory to really understand this. So
right.
It's just an accumulation of parts. But one thing I worry about is that as we describe this, again, if I take the engineer's perspective and I want to design a regulatory circuit for some system, I can always design something much more simple than what we actually observe or have described, or very often can.
Right.
And I worry about, well, does this just mean we don't understand the complexity of the set of conditions under which this really evolved in nature? And that's, I think, is going to be the tough part to really, even coming up with the abstractions of it, to really understand what were the evolutionary forces that led to this
Right.
complex behavior. And I don't know how to get, I don't know if the idea is how to get, maybe
Yeah,
something that you have, but how to get.
I agree with you. I think the part that I ignored in my talk is evolutionary forces. And I think it's a crucial ingredient in biology. And it will, if you look even at complex engineering systems, the ability to evolve the system is becoming more important than anything else. So if you create a large software system that you cannot evolve it, but you will have to write everything from scratch every time, then you are going to be in big trouble. So I think we are learning about this type of properties in engineering and that's why there is a notion of information. You look at the internet. We lost control over it. Why? Because it evolved, and it will keep evolving, and we don't know where it's going to go. But then you can look at it and say, how do I reason about it? So I think we'll see more and more engineering or open source software. We'll see more and more engineering systems where we have evolutionary forces in a way that actually then no one really knows what's going on. So I think it's very important to understand the evolutionary part. Now, the reason we actually, one of the centers in IST is Center for Design of Biological Circuits. And the reason we focus on design is because we are good in design, not because it's the right thing. If you look, I have this claim that if you look at the history of science and technology, we are at the point where the gap between our ability to design system and our ability to analyze system is the largest ever. Because we can design highly complex systems, our ability to analyze system didn't make much progress. And this gap will keep growing. So I basically agree with you. I think, I'm not trying to be politically incorrect, but
Oh, go ahead.
no, I made this mistake before. I was interviewed, they wrote some article about IST in the CalTech magazine, and they interviewed me and the directors of the different centers and other people. And for some reason, I didn't mention evolution at all, like in this talk. And no one else did. So then someone that is into the creationism versus evolution part picked up this article and used it to write a very long article that actually the CalTech initiative is supportive of creationism because they didn't mention evolution at all in the article. Not only that, they have a Center for Design of Biological System, which is consistent with intelligent design. And then, so I made this mistake again today. So,
if I can cut in, actually, Eigen, I think he's a Nobel laureate in chemistry, says that information is the most important thing. However, channel information is not what we should look at. We should look at the way that Darwin designed it. So at the end, we see some products, and through a noisy channel. And so he's saying, you can look at it through the eyes of Darwin. You have to look if you want to actually extract information. So the question is how to do it. We'll probably have to work on a very simple abstraction and try to go from there. But you can look at the biology as a deletion channel, research deletion channel, and that's what's happening. You see the final result. You want to see how much information is passed. Right. We don't know even in this case, the last talk was Sergio Verdu talk. One of the things that we don't know even the capacity of the deletion channel, very simple thing, and which is at the basic stuff in biology. I have another question.
So how the time is captured in the system?
yeah, so that's another aspect in information theory is that we don't deal with time and we don't deal with geometry. So I think if you look at the construction I showed at the end, then actually the strength comes from dealing with time in some stochastic way. That's the way we introduce universal computation. And I think obviously evolution is another aspect of time.
Yeah, well, in biological system, in gene regulation or development, there are some certain gene will turn on only at this time.
Right.
And then that's the whole branch will not be used after that point. So it's like critical time, that whole thing.
Right. So I actually feel that so biologists then are married to rate constants. They want to figure out rate constants. And I think that rate constant, which determine the rate that certain equations happen, are irrelevant. I argue with them all the time. I think that what matters is the order in which things happen and not the time, because the same circuit can work in a nematode or it can work in humans under very different temperature conditions and with time that is scaling in different ways given the temperature. But somehow the order in which those events happen is maintained. So I'm not sure if the time per se is an issue. I think they are pretty robust to that. But that's a long argument. I don't have any formal proof for that. So I think the structure is the issue. It determines the order in which events happen. The time is something we invented.
The reason that information theory doesn't work in networks is because we don't know how to handle time. Jeff.
Just out of curiosity, are the delays you introduce exponentially or merely a function of the size and number of, say, events or reactions or something like that?
So they're actually polynomial, and we make sure that when they sum, they don't sum to something too big. So it's more like 1 over n squared or n cubed, and then it takes care of itself as you sum it over time. That's a very good technical question. But we have much better simulations in terms of the efficiency using direct mappings to Turing machines. Is much more efficient than the register machines.
Unlike the electrical system, a biological system is very much interconnected. Like you can generate a body from a small cell. So in a sense, the whole is contained in a small part. So how do you go by explaining that in your abstraction?
I didn't get your question.
Like the biological system is very much interconnected.
Right.
And it is not so in an electrical system.
Mm-hmm.
So, and like from a small cell, you can like generate the whole body or a whole organism.
Right.
So in a sense, the whole is contained in a small part.
Mm-hmm.
Like there's a map of that.
Okay.
So
Yeah.
how do you go by explaining that in your abstraction?
So when I started working on neural systems, then the thesis was that actually the brain is a bunch of stupid neurons that because there are so many of them, together they are smart. This was a thesis in the 80s, emergent properties, right? So what I discovered over the years is that each cell is extremely complex machinery and very smart. So you cannot think about the cell as a component in the circuit. Within the cell, there are very complex mechanisms. And that's why you can take a single cell and evolve it to a very complex organism. So don't think about the cell as a component in a circuit. The components are inside the cell. The cell is a highly complex system. So the abstraction of the circuit are for very complex circuits within a cell. That's a way to think about it.
I think we'll let Shuki go. His voice is going down. So he will be till 5 o'clock in room 1200 if you want to see him, and he still has energy to talk to you. The next seminar is in 2 weeks, November 13th, and Ben Schumacher will talk about what is information insight from quantum mechanics point of view. So I see you in 2 weeks. Thank you very much, and let's say Shuki.
Thank you.